Hello everybody. Welcome to the next topic in physics, namely electrostatics. Okay, we've left thermodynamics behind and we're moving into electricity and magnetism, and we start electricity with electrostatic charge. Charge is a basic property of matter. It's been observed for centuries. They knew about rubbing fur on amber and creating sparks. So we've known about charge for a long time. Okay? Now, I usually start off by doing the lab, but we're doing the lab next week. So you may or may not have watched this video before you've done the lab. Hopefully you've watched the video. Let's start off by talking about everyday substances that are neutral. Well, neutral means no net charge. Okay? Which could be accomplished by having no charged particles, or it could be accomplished by having equal numbers of oppositely charged particles. We can observe experimentally that there are two types of charges. Now, let me show you. Okay? Let me play with some of our equipment here. All right, guys, turn you this way. Now, can we see the little... Yes, okay. Guys, here's a rubber rod, okay? I'm gonna rub it with bunny fur. Okay, now I'm gonna put it in there. Now, if I bring the bunny fur up close to it, notice that the rubber rod is now being attracted to it. Okay? Oh, that balloon's dead. Now I'm going to take a balloon here. Okay? I should have grabbed a second rod, but I didn't. But I'm going to use a balloon. Take a balloon here. I'm going to rub it with the bunny fur. Okay? Now, when I bring the bunny fur rod up, I want you to know. Notice it's repelling it. Okay? So the balloon and the rod must have a like charge. The bunny fur and the rod now have opposite charges. So no matter what we do, we see two charges. We see charges that attract and charges that repel. Okay? We call these charges positive and negative charge. Now, by rubbing the rod with the bunny fur, we did charge development. We took two things that weren't charged and we created objects that were charged. Okay? We know that like charges repel each other and unlike charges attract each other. And these are forces at a distance. The objects do not have to touch to interact. Okay? What this means, or what the rubbing to charge tells us, is that a neutral object has equal numbers of both types of charges. Equal number of positive charged objects and equal number of negative charged objects. Now, this means you can charge an object through friction. Rubbing is friction. Okay? We cannot charge metal by friction. Can we charge metal? Yes, but it has to be charged through a different means. Okay? Metal objects can be charged by a touch insulated method. Okay, now what do I mean by this? If I were to take a metal sphere. Okay? So I had a metal sphere here. And I were to place it on an insulated pole. So this is an insulator. That guy is metal. Now, one of the ways that we could charge up this metal object is to actually touch it with a charged rubber rod. If I touch it with a charged rubber rod, and I'll make my rubber rod red. Okay? So I take my rubber rod and I touch it. Charge will actually move off the rod and onto the metal sphere. Okay? So some charge moves off. And because this is an insulator, that charge has nowhere to go and it gets trapped on the metal sphere. So we can charge the metal sphere by touch. Okay? Now, metal is called a conductor. It's a material through which charge can move easily and can be charged by transfer or induction. Rubber is an insulator, a substance on which charge remains fairly immobile and can be charged through friction. So let me erase everything. Okay. Now, if we were to look at cross sections of a charged metal and a charged insulator, so a conductor and an insulator, you can see on the conductor everything gets spread. On the insulator, the charge is immobilized and it's just where the friction happened. Okay? Remember, both of these can be charged, but just in different methods. Now, the types of charge presence are referred to as positive and negative charge. These were coined by Ben Franklin. By convention, negative charge is the charge on a rubber rod after it is rubbed by bunny fur or wool. And positive charge is the charge on the bunny fur. Okay, also glass or acrylic rod rubbed with silk. We now know that positive charge comes from the protons in the nucleus of the atom, and negative charge comes from electrons outside the nucleus of the atom. So if we look at the structure of an atom, okay, and let me kind of shrink this down a little bit. Shrink this down. I don't know how that got to be so big. Come on, shrink down. Well, it's not shrinking. Okay, so the positive charge in an atom is concentrated in the nucleus. The negative electrons are outside the nucleus. When an atom gains electrons, it becomes negatively charged. If it loses electrons, it becomes positively charged. Okay? Now, inside the nucleus are protons, neutrons, and electrons. Approximately the mass of a proton is 1 AMU, the mass of a neutron is 1 AMU, the mass of an electron is 1/895th of an AMU. It's almost 1,000 times smaller in mass than a proton. The protons and neutrons are in the nucleus, the electrons are outside the nucleus. Protons are positively charged, neutrons are neutral, electrons are negatively charged. The magnitude of charge on a proton equals the magnitude of charge on an electron, which is 1.60 times 10 to the minus 19 coulombs. That numerical value is given the symbol E. So the charge on a proton is plus E, the charge on an electron is minus E. Electrons and protons are the basic charge carriers in nature. There are no other sources of charge other than protons and neutrons. For a neutral object then, number of protons equals number of electrons. When an electron is removed from the atom, it becomes positively charged, so number of protons is greater than number of electrons. When electrons have been added, it becomes negatively charged because now the number of protons is less than the number of electrons. Also, one of the things we want to notice is that charge is quantized. It comes in those hunks of 1.60 times 10 to the minus 19 coulombs, multiples of E. Now, when we charge something, we're either essentially adding electrons or removing electrons. You cannot add or remove protons. When we rub things and we charge them through friction, what we're doing is actually using the frictional force to break bonds. And when we break bonds, usually the two electrons that were in the bond go with one of the atoms and not the other. So you end up with a positive molecular ion and a negative molecular ion. One goes to the new object, one goes with one of the objects, one goes with the other. The law of conservation of charge says charge can neither be created or destroyed. It can only be transferred from one object to another. Okay? Law of conservation of charge says charge can neither be created or destroyed. It can only be transferred from one object to another. Now, let's look at some of the differences between conductors and insulators. Okay, conductors are materials that have a loose hold on their outer electrons. The core of the atom is made up of the nucleus and core electrons, which stay in place and are surrounded by a sea of outer electrons that are shared by the whole piece. In this case, most conductors are metals, so notice I said the whole piece of metal. Charge can flow through this material because the electrons in the valence are free to move and are not held onto tightly. Okay? So we have this hunk of metal. There's the positive cores, which is the nucleus and the core electrons. And then we have this sea of electrons, and they're moving all the time. And they don't move just in the sphere of their own atom. They're moving in between all of them. So they're moving all over the place. Okay? In an insulator, okay, guys. Okay, that's okay. 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 Now, an insulator, here we go. An insulator has the core of the atom and its valence electrons, and the valence electrons are tightly bound to that atom. Okay, these guys interact through some partial charges and some different ways to stick together, but each atom has a very tight hold on its own electrons. And the electrons are not whizzing in between. Insulators won't conduct because there aren't any electrons that are free to move through. Charging up insulators is done through friction. When the insulator is rubbed, then the molecules along the surface are broken, and they're broken up in such a way that they create ions, and one of the ions stays on one of the objects, and the other ion of the opposite charge is transferred to the other object involved in the rubbing. Charging up metals conductors must be done in a totally different manner, okay? You can do it by Conduction or induction. Conduction is when you touch an isolated, insulated metal object with a charged object, and the charge is transferred and spread across the object. Take the object away, and some of the charge on the charged object you brought up next to the metal has been transferred, and it stays on the metal. Okay? Now, when the charge is placed on the metal, it'll spread out over the whole surface, and the charge will come to rest. This is called electrostatic equilibrium. Okay? In an isolated conductor, all the excess charge is located on the surface of the conductor. Later I'll explain why. Okay? The other way to produce a charged conductor is through induction. It occurs when a conductor is connected to a ground and a charged object is brought near but not touching. The same charge on the conductor is repelled in the metal and creates a polarized object, okay, kind of like this guy here. So we brought a positive rod up close but not touching a sheet of metal. The positive charge in the metal we can think of as being shifted to the other side. What's really happening is negative charge has moved this way, so it's left a net positive charge over here. Okay, so we've created a dipole, a negatively charged side and a positively charged side. Okay, so we've kind of gotten it to bow in one direction. If you were to connect, okay, this piece of metal to ground, okay, then this positive charge, we would actually see a draw of negative charge from the earth into this metal plate to help make this negative and this positive, okay? So if you let that happen, and then you were to come in here and you were to break this connection, now the negative charge that went up onto the metal is trapped. And this is an induction. Okay? We have induced and trapped the charge. So, you break the connection to ground, you trap it. Discharging is removing the net charge by connecting to ground. So if I then took that metal object that was charged and I touched it, let's say, to a sink, the sink is connected to ground, the charge would run off. Okay? Now, it's time for us to start taking a quantitative look at charge. The first person to take a quantitative approach to looking at charge is Coulomb in 1785. By careful work, he developed the following law. Now remember, a law is just a statement of fact. It doesn't say why it's this way, it just says this is the way it is. Coulomb's law states that if two particles having charges Q1 and Q2 are a distance r apart, then the forces they exert on each other has a magnitude of K Q1 Q2 over r squared. Now notice those are in absolute value signs because all we're getting here is the magnitude of the force. Okay? K here is called the electrostatic constant. These two forces are an action-reaction pair of forces, you know, force of 1 on 2, force of 2 on 1. They are opposite in direction, act on different objects, and have the same magnitude. Okay? The force is directed along the line that joins the two particles and is attractive if the particles are opposite in charge, and repulsive if the particles are the same in charge. Now remember, E is 1.60 times 10 to the minus 19 coulombs. K has a value here of 8.99 times 10 to the 9 newtons times meter squared over coulomb squared. We're also going to get this little epsilon 0, which is 1 over 4 pi K. and it's 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. Don't worry about that one yet. We will get to it. Now, some things to pay attention to with Coulomb's law. Number one, Coulomb's law really only applies to point charges. That's an idealized material where all the charge is concentrated at a single point in space. There's no size or extension, no charge distribution. It's just a point in space. Coulomb's law applies only to electrostatic charges, charges that are sitting still. And electrostatic forces, like other forces, can be superimposable. So we can do vector addition with them. Okay? So we're going to look at some problems in the book. We're going to look at problem 13 on page 624, the end of the chapter, and then we're going to look at problem 41. Okay, so let me get the book ready to go here, and we will do problems. So, problem 13 on page 624. Okay, we're going to look at 13 and 14. Okay, as we look at problem 13, it says a 1 kilogram masses are 1 meter apart, center to center, on a frictionless table. Each has a plus 10 microcoulomb charge. What is the magnitude of the electric force on one of the masses? And what is the initial acceleration of this mass if it is released and allowed to move? So let's flip over here so that you guys can watch the board. Okay? So, we know that the magnitude of the force is going to equal K, Q1, Q2 over R squared. So the magnitude of the force is going to equal the value of K, okay, which is 8.99 times 10 to the, I think it's 10 to the 9, but the minute that I say that, I will screw up. No, I was right. 8.99 times 10 to the 9. Let me write bigger. So I've got 8.99 times 10 to the 9 newtons meters squared over coulomb squared times Q1. Well, they're both the same magnitude charge. It's plus 10 times 10 to the minus 6 coulombs times the plus 10 times 10 to the minus 6 coulombs all over the distance squared, and they're 1 meter apart. Okay? So now what we have to do is let our fingers do the tapping on the calculator. So 8.99 exp 9 times 10 exp 6 negative times 10 exp 6 negative divided by 1 squared. So I get a force of 0.899 newtons. Now I want you to notice that the coulomb squared divide out and the meter squared divide out. The only unit we're left in is newtons. So there's the magnitude of our force. Okay? Now, since these are like charges, okay, Q1, Q2, force of 2 on 1 is going to be in that direction. force of 1 on 2 is going to be in this direction. Okay? They both experience the same magnitude force, they just point in opposite direction. Now the other question we're asked is, what is the initial acceleration? Well, we know force equals mass times acceleration, so 0.899 newtons is equal to mass, we're told is 1 kilogram, times A. So the magnitude of the acceleration here is 0.899 meters per second squared. Okay? For Q1, it would be in negative x. For Q2, it would be in positive x. Okay? Now, if we look at 14, it's essentially the same problem. So I don't know if I need to run through another one. It's just kind of busy work at that point. I think you've got it. It's kind of a plug and chug. Let me swap over. Ooh, I want to do 41. Let me see if 41 is going to be more fun. Yeah, let's look at problem 41. I think we need to do a problem like this, just kind of make sure our skills are still up to snuff. Okay, if we look at problem 41. Over here. Problem 41 says, what is the force on a minus 10 nanocoulomb charge in figure 22.41? Give the answer as a magnitude and angle measured clockwise or counterclockwise, specify which from the plus x-axis. Okay? So, let's look at things. Now, I'm going to redraw the picture up here so that we can kind of talk our way through it. Okay, once the charge on the 10 nanocoulomb, the minus 10 nanocoulomb charge, there's another charge up here that's 5 nanocoulombs and it's positive. There's a charge over here that's minus 15 nanocoulombs. Okay, this distance is 3 centimeters. This distance is 1 centimeter. One of the things I need is this distance. So the first thing I'm going to do is I'm going to get that distance. So 3 squared plus 1 squared square root. This is 3.16 centimeters. Okay, your book always takes things as 3 sig figs. So if I look at this 10 nanocoulomb charge, it's going to have a force 1 up because it's going to be attracted there, and it's going to have a force 2 pointing down here. Now I want to get that angle theta. So if I think about that angle theta, this angle theta is going to be the same thing. Okay? So if I use 1 divided by 3, inverse tangent, then theta here is 18.4 degrees. Okay? Now, let's get the magnitude of force F1 and the magnitude of force F2. Magnitude of force F1 is going to be the 8.99 times 10 to the 9 newtons meters squared over coulombs squared times the absolute value of 5 times 10 to the minus 9 coulombs times the absolute value of 10 times 10 to the minus 9 coulombs. I'm not using good scientific notation, I know, but you run into that a lot when you're dealing with these charges. And the separation is 1 times 10 to the minus 2 meters squared. So force 1, 8.99 exp9 times 5 exp9 negative times 10 exp9 negative divided by 1 exp2 negative squared. So I get 4.50 times 10 to the minus 3 newtons. Magnitude of force F2 is going to be 8.99 times 10 to the 9 newtons meters squared over coulomb squared times the absolute value of minus 15 times 10 to the minus 9 coulombs times minus 10 times 10 to the minus 9 coulombs all over 3.16 centimeters squared. Oh, it's 3.16 times 10 to the minus 2 meters squared. So 8.99 exp9 times 15 exp9 negative times 10 exp9 negative divided by 3.15 exp2 negative squared, and I get 1.35 times 10 to the minus 3 newtons. Now, force 2 is going to have an x component and a y component. So force 2x is going to have a magnitude of 1.35 times 10 to the minus 3 newtons times the cosine of 18.4 degrees. So 18.4 cosine times 1.35 exp3 negative. So I get 1.28 times 10 to the minus 3 newtons. Force 2y is going to have a magnitude of 1.35 times 10 to the minus 3 newtons times the sine of 18.4 degrees. So 18.4 sine times 1.35 exp3 negative gives me 4.26 times 10 to the minus 4 newtons. Okay? So now we're going to do sum the forces in the x direction and sum the forces in the y direction. So the sum of the forces in the x direction is just going to be 1.28 times 10 to the minus 3 newtons. Sum of the forces in the y direction is going to be force 1, which is 4.50 times 10 to the minus 3 newtons, plus a minus 4.26 times 10 to the minus 4 newtons. Because force 1, positive y direction, force 2, y, negative y direction. So if I add those together, I get 4.07 times 10 to the minus 3 newtons. So force net, okay, is going to be the square root of 4.07 times 10 to the minus 3 squared plus 1.28 times 10 to the minus 3 squared. So I square square that, plus 1.28 exp 3 negative squared. Take the square root, and I get 4.27 times 10 to the minus 3 newtons. And this is going to be at an angle theta below plus x, so that would be clockwise, and theta would be the inverse tangent of y, magnitude of y over x, and y was 4.07 times 10 to the minus, actually it's above, 4.07 times 10 to the minus 3 divided by 1.28 times 10 to the minus 3. So 4.07 divided by 1.28. Inverse tangent, and I get 72.5 degrees. Okay, and that's above plus x. Now, the reason I wanted to do this one is just to remind you guys that you still have to do vector addition, okay? It's not gone. It is still lurking out there. You're still going to have to do it. Okay, let's move back over. You guys get to look at the ceiling for a sec. Okay, now, electrostatic forces like gravity and magnetism are forces at a distance, or we could call them long-range forces. And the major question that scientists had in the 18th and 19th century about long-range forces is what was the mechanism by which these forces are applied. Most scientists really had a hard time dealing with this. And especially the idea of a force being transmitted through empty space. Remember, we talked last semester about having an object and an agent. So in this case, they want to know what is the agent of the force. Okay, so if we had two statically charged particles, A and B, okay? So the force of A on B is originally pointing in this direction. Okay? If A very quickly moves to a new position, then the direction of the force A on B has to change. Also, if it's moving further away, the magnitude of that force has to change. Okay? Would the force of A on B suddenly shift? Would it matter if they were a centimeter apart, or a kilometer apart, or a light year apart? Nothing in Coulomb's law or Newton's laws of gravitational force can be linked to time. So, according to Newtonian physics, okay, the shift in charge position would have an instantaneous effect, be seen instantaneously by particle B. Okay? And scientists didn't like that. It just didn't feel right. Then in the early 1800s, a guy by the name of Michael Faraday. Now, Faraday came to be a scientist in a roundabout way. Faraday started sweeping the floors in a lab and then moved up to kind of a professor's helper and ended up learning enough to take over the lab. But the one thing that Faraday didn't get was math skills. He came to start working in this science lab when he was in his early teens, and he just never ever was comfortable with math. Now, Michael Faraday took a new approach to this. he was very good conceptually. He was very good at looking at things and coming up with physical kind of descriptions. And Faraday had been looking at magnets, okay? And he's going to take a new and interesting approach. Okay? Now, he's very intuitive, okay? He's going to look at things. Now, when we look at these two magnet setups, okay, what Faraday noticed is that when he put iron filings in between, or sprinkled them around these two magnets, where we've got a north pole facing a south pole, they formed these lines. The iron filings collected in lines, okay? And when he put a north up to a north, he got a different pattern. Okay? Faraday suggested that the space itself around those magnets was filled with some kind of magnetic influence that altered the space, and the iron filings were responding to this alteration in space. This alteration in space is the mechanism, the agent by which forces at a distance applied. Okay? This idea of altering space has come to be known as field theory. In math, okay, the fields are functions and variables of x, y, and z that assign a value in space to a value to every point in space. So in physics, when what field conveys and what field theory gets at is that there is a physical entity at every point in space, some kind of disturbance or influence at every point in space. Okay? So an object with mass influences somehow the space around it and alters it. An object with charge influences and changes the space around it. With this concept, we can say that mass creates a gravitational field, charged particles create an electric field. Okay? Note, this means that the field depends on the one object that causes the field, and something else is going to respond to that disturbance caused by that source object. Think about a bowling ball sitting on a mattress. Okay? When we sit a bowling ball on a mattress, what it's going to do is it's going to deform the surface of the mattress. So if I put other smaller balls on the mattress, they're going to roll toward the bowling ball. That's kind of how you can think about a field. Okay? It took another scientist to kind of mathematically work out field theory and kind of catch things up. When Faraday first proposed this, and he didn't have the mathematical equations to back it up, a lot of people said, we're not believing anything. Okay? So, recap. A charged particle creates a disturbance in space around it that other charged particles then respond to. It is this alteration, the disturbance in space caused by the charge, that is the mechanism by which forces at a distance work. One charged particle is called the source charge, and the other particle that responds to it is called the test charge. Okay? So every time we look at an interaction between two charged particles, we're going to look at it in terms of a source charge and a test charge. The source is going to be creating the electric field. The test charge is going to be experiencing the electric field. Now, let's look at gravity first. Okay, and then we're going to look at electric fields. Notice, looking at the force due to gravity equation, force due to gravity is G, big G, M1, M2 over R squared. It looks very much like the Coulomb's law equation, except instead of G in Coulomb's law, you'd have K and you'd have the two charges. Okay? Let's say M1 is the source of the gravitational field, like the Earth. and M2 is responding to it. If we do that, we can kind of regroup things a bit. Okay, so if I factor M2 out, then I have force of 1 on 2, the source charge on the test charge, is equal to M2 times G M1 over R squared. Okay? Now, the mass of the object 1 isn't going to change. G is the gravitational constant. Your distance could change. Now, this for the gravitational field always points in toward the center, toward object 1. Turns out that G M1 over R squared is what we refer to as little g if we're talking about objects not far from the Earth's surface. Okay? So if you're close to the Earth, you're in the Earth's gravitational field, and if your R is fairly close to the radius of the Earth, then you've got G as your gravity. Now, this value G, little g, which is big G M1 over M2, is independent of mass 2 and is only dependent on the distance object 2 is from object 1. Okay? And as long as we're close to the surface, G is pretty constant. So force due to gravity on planet Earth is mg, pointing toward the center of the massive object 1, the center of the Earth. So we've got the mass of the test object times the gravitational field strength. So G, okay, is that disturbance in space caused by the presence of the Earth. Now, the one nice thing about gravity is always an attractive force. The direction is easy to determine. It's always from the test object toward the source object along a radial line from center to center. For charged particles, the idea is the same, but the directions take a little bit more work because there are not only attractive forces when we're dealing with unlike charges, but there are repulsive forces when we have like charges. So let's go through the same type of process for point charges. Q1 we'll call our source charge QS, okay? Creating the, actually that should say electric field. Let me fix that. Okay? Q1 is going to create the electric field. For other charges to interact with. Q2 is a test charge. So we'll label it QT. And is there to test or experience the electric field caused by Q1. Now we know that the magnitude of the force of 2 on 1 is K Q1 Q2 over R squared. Now if we factor Q2 out and add QS and QT, the force of source on test is equal to the magnitude of Q test times K QS over R squared. Okay? We're going to call that E. E is the electric field, and it's equal to K, the magnitude of the electric field, the disturbance in space is equal to K, the charge source, and the location in space relative to the charge source, R squared. And that's going to equal the force that the test charge is going to experience divided by the magnitude of the test charge. Okay? The magnitude of E, the electric field, then depends on QS, okay, the source charge, and the location in space you're interested in. It's totally independent of QT, the test charge that's going to be interacting with the field. Okay? To get the direction of the E vector takes a little work. So let's start by talking about a unit vector, a new unit vector, the R vector, or R hat, which starts at the center of QS, the source charge, and points outward along a radial line. So if that's my test, this is my QS, then, okay, there's our radial line outward, and we can have radial lines going out in any direction. Okay. R hat is a 1 unit long vector pointing out along any of the radial lines. Okay? So we can say the following. The electric field as a vector quantity is equal to K, QS, where that's the charge on the source particle, over R squared, R hat. So notice, if QS is positive, so if this was a positive charge, then the electric field vector is going to point in the direction of the R hat vector. It's going to point outward. So for positive QS, E points outward. Okay? Now, if I had a negative QS, so this was negative. So if a negative QS, E would point inward because it would be negative R hat. Okay? So it's going to point in the opposite direction of R hat. So QS is positive. Electric field vectors all point in space away from QS. If it's negative, it points toward. So here's an example of some electric field maps around a positively charged particle and around a negatively charged particle. As you move out further from the positively charged particle, the strength of the electric field is going to drop off as a factor of R squared. So it's going to drop off exponentially. Now these aren't every electric field vector. If we drew in every electric field vector, they'd start overlapping. But this is just a sample, so you can see these guys are in closer. They all point out, and they're the longest, so that's the strongest electric field. Here, again, they all point out. They're a little bit smaller because we're a little bit farther out, and smaller still further out. Now, these vectors that we've drawn in are there to represent relative strength of the electric field. They are not position vectors going from point A to point B. They're just showing you relative strength. Okay? Notice here, okay, they're all pointing inward. Closer in, longer vectors. Further out, smaller vectors shown because the field is weaker. Again, field drops off as a factor of R squared. So we can say the following. Force vector is equal to the electric field vector times Q test. If we have a positive charge, then the test charge is going to experience a force in the same direction as the electric field. If the test charge is negative, the force is going to be in the opposite direction of the electric field. Okay? Therefore, an electric field is a vector field. At each point in space, there's a unique vector associated with the electric field at that point. The magnitude of the vector is an indication of the strength of the electric field. This is an abstract vector, not a displacement vector or a position vector. And the vector points in the direction of the field. Now, just like with electric forces, electric fields can be added together. So if I had two stationary charged particles, and they are going to both create magnetic fields in a region in space, their magnetic fields aren't superimposable. They can be added together. So we're going to look at problem 32, 30, and 67 at the end of the chapter. I think we're going to do problem 30 and then, let's see. Yeah, we'll do 30 and 32. Okay? So, let's look at problem 30. It says, what is the strength and direction of the electric field that will balance the weight of a 1 gram plastic sphere that has a charge of -3 nanocoulombs? Okay, so let's start by drawing a pretty picture, because we always need a pretty picture. Okay, so we have a little sphere here, and it has a force due to gravity pulling down on it, okay? And it's going to have a force electric that's going to have to push up on it, okay? Now, things that we know about this guy is that our mass is 1 gram, so it's 1.00 times 10 to the -3 kilograms. And its charge, okay, and I'll label it QT because this is what's going to be experiencing the field, is -3.0 times 10 to the -9 coulombs. Now, since the force electric has to be up, that means that I have to have some kind of negative charge down here, okay, to create that force upward. Okay, so I know that my electric field is got to point upward. Now, I could also say that I had something positively charged up here that's pulling it. I don't know which one is which, so I'll make it a positive charge up there, ground down here. Now, it asks us what's the strength and direction of the electric field that will cause this to balance. We know then that the sum of the forces in the y direction have to be 0. Our force due to gravity in magnitude is going to be equal to mg. So it's 1.00 times 10 to the -3 kilograms times g, which is 9.80 meters per second squared. So it's 1.00 times 10 to the it's 9.80 times 10 to the -3 newtons. Okay? So, our sum of the forces in the y direction, force due to gravity, force electric, have to add up to be 0. So I have a minus 9.80 times 10 to the -3 newtons plus force electric equals 0. So force electric is 9.80 times 10 to the -3 newtons. Okay? force electric equals QT plus times E. And we're just looking for the strength and direction of the electric field. Force electric is in the positive direction. It's 9.80 times 10 to the minus 3 newtons. And that has to equal the charge, minus 3.0 times 10 to the minus 9 coulombs, times E. Okay? So if I solve for E, I'm going to take 9.8 exp3 negative divided by 3.0 exp9 negative, and I get 3.27 times 10 to the 6, and that's newtons per coulomb. Okay, and it's negative. Now that negative sign is important, okay, because if we think about this in terms of this being a positive charge up here that's interacting, we know that the electric field from a positive charge would be pointing away from it along that radial line, which in this case would be down. If it was a negative particle doing it, the negative particle, the electric field vectors always point toward. So it makes good sense. The direction of this electric field is in the negative x direction with the way I've set up the system. Okay? Can we handle that? All right. Now, let's see. The other problem I had picked out was problem 31 and no, problem 32 and problem 67. 32, you can do that. It's just kind of boring. Let's look at see if 67 is fun. Yes, 67 is a fun one. So we're going to look at problem 67. Okay, guys, let's come over here. If we look at problem 67, it says the electric field E is 100,000 I newtons per coulomb, and it causes the 5 gram point charge to hang at a 20-degree angle. What is the charge on the ball? Okay, well, let's do a free body diagram here. Okay, so if we look at the ball, there is a tension force, force due to gravity, and force electric. Okay, so those are the forces acting on the ball. And we know that this was a 20-degree angle. So that means that this is a 20-degree angle. That has to make this a 70-degree angle. Okay? Now, our force due to gravity is going to be the mass of the object, which is 5.0 times 10 to the minus 3 kilograms times 9.80 meters per second squared. So force due to gravity, 5 exp3 negative times 9.80. So 0.0490 newtons. And the tension force I don't know, but I know that there's going to be a Tx, and Tx is going to be T cosine of 70 degrees, and Ty is going to be T sine of 70 degrees. Okay? Now, the only force that I know is my force due to gravity. So I'm going to look at my sum of the forces in the y direction first. So I'm going to have force due to gravity plus Ty, and that's going to sum up to be 0. So I have a minus 0.0490 newtons plus Ty, which is the magnitude of T, sine of 70 degrees, having to add up to be 0. So T is going to equal 0.0449 divided by the sine of 70 degrees. So I get 0.0521 newtons, okay, as the magnitude of T. Now, what does that do me? Well, once I've got T, I can get the magnitude of Tx. The magnitude of Tx is just T cosine of 70 degrees, so 0.0521 newtons cosine of 70 degrees says that Tx has a magnitude of 0.178 newtons. Now, think about Tx, it's here, okay? There was my Ty. So if I look at the sum of the forces in the x direction, I have force electric plus Tx having to add up to 0, force electric plus a minus 0.0178 newtons equals 0. So force electric is a plus 0.0178 newtons. Okay? Now, the thing that we were asked to find here is what is the charge on the ball. Well, our force electric has to equal Q test, which is the Q on the ball, strength of the electric field. Force electric was a 0.0178 newtons, and that has to equal QT plus the strength of the electric field, which we're given was 100,000 newtons per coulomb. Okay, and it's positive. So 0.0178 divided by 100,000, and I get QT to be a plus 1.78 times 10 to the minus 7 coulombs. Okay, I wanted to do that one because I wanted to get you guys to think about the fact that you got to break your forces up, look at the sum of the x's, look at the sum of the y's. Okay guys, this ends the chapter, and you are now well on your way to electrostatics.